Hello everyone. The purpose of this video is to walk through a couple of examples of alpha-beta pruning. Hopefully these examples will be fairly substantial so that you'll get a good feeling for how alpha-beta pruning works. Before we walk through the examples, let us recap what alpha-beta pruning is. So the idea is that if you're in a game tree and you're doing MINIMAX, and let's say you are at a node n, and let's assume that this is a min node, and similar argument would work even for a max node, but for the purposes of this explanation, let's assume you're at a min node. So for example, you're at this min node here, this n min node at the bottom, and you're trying to calculate the value of that min node. And since it's a min node, the way you calculate the value in MINIMAX is you look at all its successors and try to find the minimum value across all these successors. So that's what traditional MINIMAX does. Now suppose you know that in the path going from that node to the root, like if you look at the parents of that min node, well, clearly in MINIMAX, if there is a parent, the parent is going to be a max node. And if it turns out that that max node had a value, the best possible value that has been achieved by that max node or by that max agent, the best value that has been seen by that max node so far is alpha, right? Then that alpha represents a lower bound because that max node above this min node is always going to be trying to maximize. So whatever new value it picks up, that has got to be at least alpha. So it's going to be greater than alpha. And when you're trying to calculate the value of that min node, you're going to be looping through the successors, and if you happen to find a successor whose value falls below alpha, right, then obviously this min node, it's trying to minimize, so whatever value it's going to see beyond that has got to be at most that value. And so if whatever value it found happens to fall below alpha, then that means you don't need to explore any of the remaining successors of that min node, right? And that's exactly what's written here. You are looping over the n's children, trying to estimate the minimum. Let's say Vn is the value that you've estimated so far as you are going through the successors of n, and if Vn becomes worse than alpha, then you can prune, meaning you can stop considering the remaining children, because whatever values the remaining children have, the value of n is going to be at most Vn, but the parent, which is alpha, which happens to have be greater than Vn has fallen below alpha, and since the parent is going to only look at values that are at least alpha, it's going to ignore that Vn. It's going to ignore whatever other value that comes for Vn, right? So that's why you can prune, you can ignore it. And the max version is symmetric, right? It's exactly the opposite. And let's just kind of briefly recap the pseudocode for MINIMAX. If you are at a max node, meaning if you're at a node or at a state where a max agent is going to be acting, the max agent is going to try to compute the max value of that state, and assume that you already have an alpha and beta, alpha being the minimum, the best that a max agent can do, right? So whatever other value that the max agent is going to find is going to have to be at least alpha, greater than alpha. So alpha is a lower bound for the values of that max agent. And beta is an upper bound, which means that any min agent is going to, while it's minimizing, it's going to any value that it finds is going to be at most beta, right? So you keep passing in this alpha beta as you go down in your recursion, and the max value of the state at alpha beta, it returns a utility value, which will be that max value. And the way the code goes is that if your state happens to be a terminal state, then you can just return the utility of that state. You don't need to explore any further. You don't need to do anything else. Otherwise, since you're trying to maximize, you start by assuming the worst. So you start by assuming that the value of that node is minus infinity. And then you go through the successors of that state. I mean, these actions and result essay, they're all basically finding the successors of that state. You go through the successors of that state, and you set the value that you've calculated so far, the new value adjusted to be the maximum of the current value and the value of the successor state, right, that you just encountered. And the value of the successor state is going to be a min value because it's a min node, right? And you're just passing in the alpha beta parameters down to that min value of those successors, right? Now, in the process of maximizing, if you exceed the upper limit, if you exceed beta, then you can just return V. That means you don't need to explore anymore the successors of that max node, right? This is basically based on the same argument that I just gave, except that I was giving that argument for the min value. It's just the same symmetric argument. So if you're at a max node, you need to worry about the upper limit. You need to worry about beta. You need to make sure that, if you exceed or match or exceed beta, you just don't explore any further. That's when you can prune. If you happen to be below the upper bound, then you just adjust your alpha, the best that you've done so far, in case the V that you found was greater than alpha. If the V that you found was greater than alpha, then that should become your new alpha for the next successor, right? As you keep going, you're also adjusting the alpha, and you are going to be using it for the next successor. And then, of course, when you return the value, this maximum value that you found so far across the successors, excluding the ones that you did not explore because of pruning, right? And then, of course, the one thing to keep in mind is that when you are when you've adjusted these alphas, but when you return, that alpha will be popped off the stack, right? And so the alpha will not really change. So that's these alpha beta are not really going to change in this function when you pop out of that. Okay. All right. So that is the max value, and the similar logic applies to the min value. When you're doing a min, you need to worry about, did you fall below the lower bound, which is, did you go below alpha? And if you did, you need to then return that, right? And if you fall within the range, if you're above alpha, then you just need to make sure that you pick up any other value of v that happens to be lower than beta, right? So if you get a v that is lower than beta, that becomes your new beta, right? And then you return. Okay, so let's use what we've just learned to solve this particular example, right? So let me just make sure that my typing will show properly. Sorry, let's just go back here again. Let's go here, and okay. So there we are. So when we start off, when we're at the root node, the max node, we start off with alpha equal to minus infinity and beta equal to infinity, right? And this is the lower bound. The lower bound for a value is minus infinity. The upper bound is infinity. And you can represent that in a short form as minus infinity, infinity, right? Okay, so just as in depth first search, you're going to do recursion. So you're going to be calling the max value on this one, which is then going to loop through these successors and call min value on them. And when you're calling min value on this, you're going to be passing these values down. So this is going to be passed down. And then this min value is going to call max value on this, which will also be passed down, right? And then finally, this max value is going to try to maximize across its children. And when you're going across the children of a node where you know that the upper bound is infinity, then you can kind of make your life a little bit easier and simply say, you know, I'm going to blindly go through all the child nodes and take their maximum. Why? I don't need to look at it one by one and sort of go up and down when I'm solving the problem, because I know that I'll never exceed infinity. I'm in a max node. I'm trying to maximize. The upper bound is infinity. I can never go above infinity. So that means I'm going to have to explore all the child nodes. There's no sort of pruning possible when your upper limit is infinity. So just take the maximum. The maximum of this is 2. So this is 2, right? The value of this max node is 2. If the value of the max node is 2, that means that the best value that is possible for a max node is 2. So your alpha is going to be 2 here, right? Which, again, it doesn't really do anything for you to put 2 here, but it's just, indicative. It's not going to help you with any pruning at this stage, but it is useful for you to know that, okay, that's the best I've done so far, right? Okay. Now, I would need to go to its parent, right? Because I want to now loop through the successors of the parent here. Parent is a min node, right? Now, when I go to the parent, which is a min node, so far I've seen a value of 2, which is the best possible min value. What does it mean to be a best possible value for a min node? It means that whatever other value you might see or that you might be interested in is going to have to be at most 2, right? So that means the best value that I've seen so far is 2, means beta is 2. And so I can now change this and make the beta to be 2. My alpha is not going to change. my alpha is still going to be negative infinity, right? So the alpha is like the best that a max node is going to do across its parent. Well, that is still minus infinity, right? Even though you got an alpha here of 2, that has no relevance to the alpha that you get at a min node, right? Okay, so this is the these are the ranges of values when you are at this min node. And then when you are going through the recursion again, so when you're doing the recursion, you're doing a min value. You're doing a min value, which means you're going to do min across the max values of your children. If you're going to do min across the max values of your children, when you're doing a min, you have to worry about, do you ever fall below alpha? Well, if alpha is negative infinity, right, then what you can be sure that you're never going to go below negative infinity. So you might as well look at the minimum across all these values, right? So the minimum across 2 and 2 here is 2. And then I need to figure out what is the value here, because I'm going to take a min against that, right? I'm going to just blindly take a min against that. So I need to know what is the value of this particular max node. Because if it so happens that this particular max node has a value smaller than 2, then that is interesting to me, right? I'm gonna honor it. If it's greater than 2, then it's not interesting. That means I'm gonna have to prune it, right? I'm gonna do some pruning. So let's see what is the possible max value. Now, when you're doing a max, so you pass the limits down here. This is minus infinity 2, right? When you're doing a max here, what are you worried about? You're worried about your max exceeding 2. That's something that you have to check, right? So how do you check that? You go through the children and you look at the value of the successor of the max node. You check if it is greater than beta, if it's greater than the upper limit. When you're maximizing, you're always worried about, did you go above the beta? So what is the value here? The value here is 4, right? So when I come back here, the best value that I've seen so far is 4. And 4 is greater than 2, right? So if you go back and look at the code, if your V is greater than beta, then you can return that value of V and you can prune the remaining successors. Basically ignore the remaining successors, right? So you return the value 4, right? You basically stop exploring. You say that this is what I'm going to assume the value is. It's just 4. And that's the best value I got so far. Okay. So if the best value I got so far here was 4, and I am trying to now minimize across 2 and 4, whatever the value is of this max node. For example, here, this could have been higher. Instead of minus 3, this could have been something else. It could have been 7. And of course, if we ignore the fact that we pruned here, if this were 7, this would have been, a value would have been of 7. But the parent of that node doesn't care. The parent of that node is minimizing, right? So that's the point, that this value is going to be at least 4, right? And this value has already found a 2. And so this guy is going to be at most 2, but it already found something that is 4 here. It's going to ignore that. So this value, min value, is 2, right? So this has a value of 2. So, okay, so the min value here is 2. And now we can go up here. Okay, so I'm going to continue where we left off. My video stopped for some reason. So let's continue. So when I go to the parent, and I find that I've gotten a value of 2 here. And I'm a max agent. So what do I worry about when I'm a max agent? I worry about when I'm trying to maximize. Did I ever exceed beta? Well, I can never exceed beta. Beta is infinity. But that means I'm going to pick this value, and that's going to be my alpha. That's the best I've done so far, right? That means now my alpha becomes 2, right? And what does it mean for alpha to be 2? It means that this alpha of 2 is now going to be honored here, right? This min node is going to consider the fact that a parent max node has found a value of 2, and so it needs to take that into account, right? So when I come down here, as I'm looping through, when I come down here, I will pass down the value of 2 infinity as my range, as my interval, right? Okay. So, okay, that's fine. I'm a min node. Min node means I'm going to be trying to minimize. So I come down here, I find a value of 3, and I'm trying to minimize. So when I'm trying to minimize, I am interested in knowing if I fell below my alpha, if I ever went below my lower bound. Well, it's 3 here. So 3 is higher than 2. So I'm not going to return. I cannot prune. But what it does mean is that my alpha needs to be adjusted. As far as this particular recursion is concerned, for the purposes of analyzing the remaining successors, I better adjust my alpha. So my alpha here becomes 3, right? Okay, so when I come down here, I have my interval gets passed down to 3 infinity, right? This gets passed down to 3 infinity. So let's see. So this is coming down. It's a max node. The lower bound is 3, and upper bound is infinity, right? And when I'm maximizing, what am I worried about? Did I go above infinity, right? Well, I can never go above infinity. So I might as well take the max of 1 and 0. Max of 1 and 0 is 1, right? So my value here, right? The value of this node is 1. And that means when I'm going through this min node, I found a value that is lower than 3. So from the point of view of this node, I've fallen below 3. So I return that value of 1. And now I can prune this node. I don't need to bother exploring the remaining node because I have fallen in the process of minimizing. I have fallen below alpha, right? Okay, so let me clean this up a little bit here. So let me just take this out here. Basically, my 1 has fallen below 3, and so I'm not going to explore this child node anymore. So let's just clean this up as well. So this was 3 infinity. When I came down here, remember, I am not going to be adjusting the alpha when I'm looking at the children of a max node. And in this case, I found a value which is less than alpha, so I return that value. So when I return that value, I'm going to consider that the best value that I got so far, taking into account the fact that I'm going to ignore the remaining children, is 1, but I can prune the remaining nodes. And so this value, as far as its parent is concerned, is 1, right? Okay, so let's also clean this up a little bit. So this is to infinity, right? I just clean this up a little bit. And this is to infinity. Okay. So I'm in a max node. I'm trying to maximize. I got a value of 1. 1 is lower than 2. Who cares? This is a max node. The fact that it fell below, that it has a value, there's a value below 2, doesn't matter. It's not even going to look at it. It doesn't care about that value here. It's going to say, oh, this value is lower than what I've seen so far. My best value is still 2, right? Okay, so now I'm going to go explore the last child of this max node, okay? So I come down here, and when I come down here, I need to pass the to infinity down, the alpha beta get passed down into this min value of this, right? So the min value of this, it's going to call the max value on this. So that gets passed down. This is also to infinity alpha beta. So now you've got a max node where there is where the upper limit is infinity. And again, you sort of can blindly make decisions on what you need to do here. We don't need to really worry about saying, oh, I need to go up and down. You've got a max value, the upper bound, a beta of infinity. So if the beta is infinity, when you're maximizing, you're never going to exceed infinity. So you can happily just take the maximum of this. Max of 3 to 3 is going to be 3, right? There's no pruning possible here for this node. So I got a value of 3. However, this becomes very interesting for this min node. The min node says, okay, I found a value 3, okay, and the value of this 3 is right. Actually, no, this one, there's no pruning here as well. So the value here for a min node, it didn't fall below 2. It stayed above 2. So, and it's well below beta. This is a min node. So the best that happens here is, because it's a min node, the upper limit is actually now going to be 3, right? So the upper limit is 3 now. So this is going to be 2, 3. And so when I come down here, I'm passing in 2, 3, right? I'm in a max node. Max node, what do? I look at 0. 0 is less than 2, but doesn't matter. We're looking at a max node. Who cares? It's never going to be considered. It can only be greater than 0. And the next one is 2. And 2, lies below 3, and the max of 2 and 0 is 2 anyway, so this value is 2. So nothing changes here, right? And so now the min of 3 and 2 is 2, right? And so if you're doing a max across, you couldn't prune anything here, so you just literally have to do a max across these child nodes, and the max is 2. So the only pruning you could do was for these 2, okay? All right, let me pause the video here, and then I'm going to tackle a new, another example, a more complicated example. Okay, now let's look at the second example. Here's the game tree. It looks it's a little bit more complicated than the previous example that we saw. And obviously, if you have an opportunity to prune, you would be you would get a lot of benefit from pruning here. Because this looks like a slightly more complicated, game tree. Some of these spaces here are actually suggestive of where the pruning might happen, but we're not going to go by that. We're going to actually calculate it, right? Okay, so let's go through it. We're going to go faster this time. So we start off at the root, and we have the interval of minus infinity plus infinity here. We pass that down, and that is going to carry over further down, which is going to carry over further down. And unfortunately, in this example, this is an example from an example online. They're not following the convention of having upside down triangles for min nodes and regular triangles for max nodes. So sorry for that. We're just going to have to kind of refer to the text on the right to know whether we are at a min node or a max node. Okay, so just keep that in mind. Okay, we come all the way here, and we are at a min node, right? And at a min node, the range, of course, that's passed in is minus infinity, infinity down here. And this is a min node. It's going to try to minimize across its children. When you're trying to minimize, you're always making sure that you don't fall below alpha, which is the lower bound. Lower bound is minus infinity. You're never going to go below that. So you can merely take the actual minimum. The minimum is 5. So the beta is going to be 5 here. So let me adjust that and put beta equal to 5. Okay. So that means my interval now is going to be minus infinity 5 here. Okay. And I am going to be then going up to its parent because I need to look at its peer successor. So that means I need to go to the parent. The parent is a max node, right? It's a max node, and when it's a max node, you're trying to maximize its range is definitely the upper bound is infinity. And when it came, it was minus infinity. The alpha was minus infinity. The beta was infinity. I just found a value of 5, right? So the value of this node is 5. And so that's the best value for this max node. So my alpha is going to be 5. By the way, all the nodes in here have values. So, those are values that are coming from doing a full-blown min-max. We're going to ignore those values for the time being. We're not going to go by the values that are printed on non-leaf nodes. We have to calculate them. We have to estimate them as part of doing alpha beta, pruning, min-max with alpha beta pruning. Okay, so now my alpha is 5 and beta is infinity. And what good is this alpha? Well, this alpha is, I'm at a max node. Alpha really, the only thing that matters is, you might adjust your alpha if there's lots of nodes when you're looking through. But beyond that, alpha is not what you are going to look at when you're trying to maximize. What you're going to look at for pruning is beta, whether you've exceeded beta. And that cannot happen because beta is still infinity. Okay, so we come down here and we found a value of, whatever the value is here, ignore this value. You don't know this yet. We come here, we are at 5 infinity. Okay. We are at 5 infinity. And this is a min node. This min node is going to try to minimize across its children. And when it's minimizing across its children, it has to consider whether any value of its children has gone below 5. If it's less than 5, right? That is the trigger for pruning. Well, let's look at the first child value. It's 7. 7 is greater than 5, so that's okay. So I need to continue to explore. So I look at the next successor. The next successor has a value of 4, and 4 is less than 5. What do you do at a min node? If you go below alpha, you prune. That's when you prune. You return that value. You literally return that value. When you return that value, that means you're no longer in the loop, in this loop. So that means this has a value of, this min node has a value of 4, right? That's the estimate, value of 4, and I can prune this branch, right? So I've found one opportunity for pruning, right? Okay. Okay, so in this min node, I got a value of 4. Alpha doesn't change, right? Alpha is still 5, but I have a value of 4 here, and now when I go back up, right, I'm at a max node. The max node is going to be maximizing across 5 and 4. The beta, the upper limit, is still infinity. That doesn't change. And if you're going to be, if your upper limit is infinity, you can just blindly take the max, right? Don't need to worry about ever exceeding infinity. So the maximum of 5 and 4 is just 5. So the value here is 5. So the best value seen here is 5. Okay, now you are at a min node here, right? Let's ignore the value that is given there. You are at a min node here, and the value here is 5. And at the min node, what is the range? Well, you're at a min node. So far, you've seen a value of 5. So whatever value you're going to pick up when you look at the other node, it's going to be at most 5. It has to be at most 5. And so the beta now gets adjusted to 5. The alpha doesn't change, right? The alpha is still minus infinity, right? Alpha is coming from its parent, right, in the recursion. So we have negative infinity 5 as the limit, right? And I'm a min node. So I'm going to try to minimize. Okay, now when I'm trying to minimize, can I ever go below minus infinity? I can never go minus infinity. So you can blindly look at its children. Now this particular child, right, even if I had not considered the value here, I can just look here. There is no branches here. It's just, it's all one value, 3. So I might as well, set the value to 3 here. So I'm doing a min over 5 and 3. So the minimum is going to be, so min over, well, I come down here. This was minus infinity 5. But I am doing I pick up the value of 3 here. So minimum is 3. So if I were to adjust this, right, I have to adjust my beta because I found a value that is smaller than 5, 3. So this value better be 3 then, right? This beta is going to be 3. Okay. So minimum of 5, 3 is 3. This has a value of 3. So let's has a value of 3, right? And now when I go up, so I'm going to be now looking at the peers of this 3, and so I go back up, right? Okay, so the best value I've seen so far is 3. So when I come here, right, when I come here, the alpha now is going to change to 3, because that's the best value I've seen so far at a max node, right? So that alpha is going to be now used in this loop when I'm going through this node and this node, okay? Okay, so let's calculate, the value of the next child and see if it is greater than 3, then we'll honor that. So let's come down here. Again, ignore this value, right? Okay, so I come down here, a priori, I don't know any of this, a priori, okay? I'm going to calculate that, I'm going to estimate that. Okay, so I come down here. What is my range? It is 3 infinity, right? And that 3 infinity is going to come down here. But this particular node, you can treat it as a terminal node because it doesn't have, wait a minute, let me see. No, this one is a terminal node, not this particular guy is a terminal node. So I can treat this as 6. This is reasonable, right? This min node has no children, so its value is 6. But these guys, I need to keep them like this because I have, for this node, I have 2 children. And this is a min node, and I have to minimize across these 2 children. When I pass this, I have a value of 3 and infinity. So when I'm minimizing, I do have to worry if I fall below alpha, below 3. So I need to make sure that I don't fall below 3, right? So let's go down here and let's estimate what the value is going to be. Okay, this is a max node, right? This is a max node. This is a max node. And when I go through its children, so I pass down 3 infinity. When I look at its first child, that has a value of 6. Okay, 6, for a max node is greater than 3. So I can adjust my alpha. My alpha becomes 6 infinity, right? So let's do that. Let's clean it up here. I'm going to clean this up, right? So I want to hide this right now. I'm going to hide this as well. So I come here, I encounter the value 6. When I encounter the value 6, the max value here becomes 6 infinity, right? I did not exceed infinity for the max value. In fact, the max value is going to be max of this and this, right? Of this and this. But I don't know what this value is. But I at least know that the best value is 6. So now I'm going to explore the next guy. When I come here, my alpha beta is 6 infinity. Okay, but I'm at a min node here, right? So this is a min node here. So when I'm looking at this min node, and I am looking at its child, I find that there is a value called 6. Well, if I get a value of 6, that is equal to alpha. When I'm minimizing, if I ever become equal to or less than alpha, then I prune. Then I return the value. So the value I return is 6, and I prune this value. So I don't need to, sorry, not that one. I pruned the wrong one. Is that right? I'm here, I prune this. Okay, so this is pruned. This 6, 9 branch is pruned. Okay, so I return the value 6 to this max node, and the max I can assume has a value of 6 now. So this is also 6. This is a value 6, and that's why that's correct, right? Let's clean it up a little bit here. Let's remove this. It's not too cluttered. Okay, so at this min node, I found a value of its successor to be 6. So when I am minimizing, whatever value I see beyond that has got to be at most 6. What does that mean? That means that, so I'm in this min node. I've got a value of 6. Its upper bound has to be 6. Its upper bound has to be 6. So I change the upper bound of this to be 6. Okay, so now I'm in a min node, I'm going to look at the, in a min node, I adjust the beta, but I don't, worry about, so I'm still above alpha, right? So that means I can't trim yet. I have to look at the next node because I'm at a min, who knows, it may have a smaller value here, right? So let's look at this, its child, and see if I get a smaller value. Well, this one is a terminal node, right? There's just no branches here. So you can just assume this is 7. This is all 7, right? So this one is an easy one. And you're in a min node, min of 6 and 7 is going to be 6. So the value of this node is also going to be 6, okay? And you got 3, 6 here. So far, at a max node, you've got 3, and then you got 6. Let me make sure that I hide all of this. We don't want to see this yet. These values were calculated, right? Oops, not that. Yeah, we only want the values of the terminal nodes. These we don't want yet. We don't want to jump the gun, right? Okay, so yeah, this did not really contribute much to the value here. We've got a value of 3 and 6. Now we are at the max node. Okay, if you're at a max node, then you're worried about whether you're going to exceed the upper limit. The upper limit is infinity, so you're never going to exceed the upper limit, right? So you might as well pick up whatever new value you get here as your best value, which is alpha. So your best value is now going to adjust to 6. Because 6 is greater than 3, so your best value, so it is, you're going to do this, and your value is 6 here, right? So your alpha is 6. So your range is 6 to infinity. Okay? So let's write that clearly here. Let's write that here. This is going to be 6 infinity. That is going to be my new range. Okay. So I'm at 6 infinity. At a max node, when I was maximizing, I did not go above the upper bound, which was infinity, obviously. So I have to explore the next successor, obviously. So the next successor is a min node. Now, as a min node, I'm going to look at its children. And now, thankfully, there are sort of lots of terminal nodes here. And so this one, I can just assume is 5. This is also a terminal node, right? That does no branches. So literally, this is 5. Sorry, my video just stopped for some reason. Let me just finish this example. Okay, so here's where we were. I'm at this min node. When I come to this min node, the range is 6 infinity. And I'm minimizing. And when I look at its children, I find a 5. A min node found among its successors a value that is smaller than alpha. 5 is smaller than alpha. If 5 is smaller than alpha, what do? Alpha was 6. That's when you return. You return from this value, return a value of 5, right? And you don't need to explore any more children, so you can prune this. So it doesn't matter what the values are of these nodes. They're just not relevant to this whole min-max problem, right? So I return the value of 5, and this min node is going to have a, the best value that this min node got was, of course, 5. But it doesn't matter from its parent's perspective, because now you're taking a max across these 3 values, 3, 6, 5. Your max was infinity. You can never exceed infinity. You can just blindly take the max here. So the value of your root node is 6. That's how you get 6, right? So you pruned this branch, this branch, this branch, and this major branch, right? So this whole branch gets pruned, and that's the benefit of doing alpha beta pruning. So let me stop here.